Alright, welcome back everybody. In the previous video we talked about enzymes. Enzymes are biological molecules that speed up chemical reactions. Usually people think of enzymes as specific protein molecules that speed up specific chemical reactions. Turns out that sometimes there are enzymes that speed up chemical reactions where there are special small molecules that kind of stop the enzymes from speeding up chemical reactions. This is kind of a dumb phrase. I'm calling them anti-helpers here. Nobody really says that. Usually a molecule that stops an enzyme from speeding up a chemical reaction is usually called an enzyme inhibitor. So here's the definition of an enzyme inhibitor: a molecule that prevents an enzyme from catalyzing whatever chemical reaction it catalyzes. There are two kinds of enzyme inhibitors. First kind is called a competitive inhibitor. The other kind, believe it or not, shocker, it's called a non-competitive inhibitor. Competitive inhibitors work like this. So let's pretend this is our enzyme, and I'm going to keep this very simple. There's our enzyme. This little notch here, that little divot, is the active site of our enzyme. If you remember, the active site is the part of the enzyme that has the shape that matches the shape of the reactant, which is also called the substrate. So let's pretend that our substrate or our reactant has this shape and it fits in there, and the active site converts this little triangle thing, converts the pizza slice into some new molecule, right? That's what the enzyme does. But imagine that you had some other small molecule that had a similar shape to this, similar shape to the pizza slice. Maybe it's an ice cream cone, something like that. And this can fit in the active site as well. But if the ice cream cone fits in the active site doesn't know what to do with it. It just sits there and sort of clogs up the site and prevents the enzyme from doing what it normally does, which is to take the pizza slice and do something with it. But if I flood the system with a bunch of ice cream cones or a shape that's similar, then it's just going to clog up the enzyme and stop it from working. What this ice cream cone molecule is doing is it's competing with the pizza slice molecule for who can fit in there. And if it's competing with the other molecule for who can fit in there, and because it's competing with it, it shuts off the enzyme, and it's called a competitive inhibitor. So that's a pretend example of a competitive inhibitor. And usually competitive inhibitors have a shape that is similar to the shape of whatever it is that they're competing against. Just to give you a real example of a competitive inhibitor, there is an enzyme in all of our bodies called cyclooxygenase 2, and the abbreviation for cyclooxygenase 2 is COX-2. So there's an enzyme in our bodies called COX-2, and I forget the exact reaction that it catalyzes, but pretend it's kind of shaped like the one before and it's got that little weird shaped active site. There's some molecule that our bodies make that can go into the active site, and the COX-2 enzyme can take that molecule and convert it into some new molecule. Again, I don't remember what the new molecule is, I don't know what the reactant is, I don't know what the products are. Whatever the new molecule is, it makes us feel pain. You can imagine that it's important to feel pain, right? You put your hand on a hot stove, your body gives you a sensation of pain so that you take your hand away before you do too much damage. So the COX-2 enzyme is important. It helps us feel pain. The problem is that as a lot of people get older, this enzyme goes a little crazy and it makes too much of this molecule. It makes us feel pain, including a lot of situations where we don't necessarily need to feel pain. And a lot of times this feels like arthritis pain when the COX-2 enzyme goes crazy. What people have done is they have designed molecules that look a little bit like this molecule. Let's pretend that it's a snow cone or an ice cream cone. And you can eat this molecule. If you eat enough of it, it will go to the COX-2 enzyme and basically sit in the same spot and compete with the other molecule for who can sit there. And it will make the COX-2 enzyme less effective, which means we will feel less pain and the arthritis pain goes away. And there are many molecules that work like this, and they include aspirin, ibuprofen, Aleve, I forget what Aleve is, maybe that's ibuprofen. Aspirin, ibuprofen, Celebrex, there are many different that we actually take as medicines that are competitive inhibitors for COX-2, and this is how they work. They compete with whatever normally sits in the active site of COX-2 to stop it from working. Non-competitive inhibitors are a little bit weirder. The way a non-competitive inhibitor works is, let's pretend here's an enzyme. This little notch there is the active site. But there's another part of the molecule, somewhere else, that has a different shape. Whatever that part is that I'm pointing to right now, that's not the active site. But you can imagine that there's another molecule that has a similar shape to that, and it can fit in there. And once it fits in there, it distorts the shape of the active site. And it distorts the shape of the active site so much that whatever normally sticks there, or pizza slice, just can't stick there anymore because the shape got completely messed up. If you have this kind of molecule that stops the enzyme from working, it's called a non-competitive inhibitor. So I want you to know the difference. Non-competitive inhibitors stick to a place not on the active site, and they distort the shape of the active site. Competitive inhibitors just compete with whatever is normally sticking to the active site, but they both end up making the enzyme work less effectively. And I have 2 videos or 3 videos to show this to you in case this does not make any sense. Alright, in this first video what they're going to show you is just a regular old enzyme. They're going to show you a regular old pretend enzyme with an active site speeding up a chemical reaction. Here it is.
During the normal enzyme catalytic cycle, the substrate encounters an enzyme with a specific active site to which it binds, forming an enzyme-substrate complex. The enzyme then facilitates the breakdown of the substrate to its products, which part from the enzyme, leaving the active site free to catalyze another substrate as the cycle begins again.
There you go. There's the normal reaction. This is the enzyme here. This is the reactant or the substrate, and this little carved out shape here, that's the active site. Now in the next video they're going to show you what a competitive inhibitor does.
Competitive inhibition occurs when an enzyme encounters a block.
If you notice, the competitive inhibitor, this is the competitive inhibitor over here, it has a shape that is similar to the active site, or at least a shape that's similar to part of the active site.
Which mimics the properties of the substrate and binds to the enzyme's active site. Thus, when the substrate is encountered, the active site is not available for attachment and no reaction will occur.
So that's competitive inhibition. Here's non-competitive inhibition.
Non-competitive enzyme inhibition involves the binding of a blocker to the enzyme away from the active site. This binding causes a conformational change in the enzyme, altering the shape of the active site, which prevents the substrate from binding. No reaction will occur as long as a non-competitive blocker is bound to the enzyme.
Just in case you're confused, conformational change just means change in the shape of the molecule. And that's non-competitive inhibition. So that's it. As far as this material, there is a lot of material. Things that you should know. You should know the general features, the chemical structures of amino acids. You should know where the amine group is, the carboxylic acid group, side chains, etc. You should be able to recognize different amino acid side chains as long as you can consult your book. You should know what an enzyme is. That's a biological molecule that speeds up a chemical reaction. You should know what protein denaturation is. That's when the protein unfolds and doesn't do whatever it's supposed to do. You should know what optimum temperature is. You should know what pH optimum is and what it can tell you. You should know what competitive and non-competitive inhibition is. You should know what primary structure means when you're talking about protein molecules. You should know that there are different categories for amino acids. There are hydrophobic ones, hydrophilic ones. Which ones are they? You don't need to memorize that, but you should be able to look it up in your book. You should know which types of amino acids are usually found on the interior of a protein molecule, which ones are found on the surface usually. You should know what an active site of an enzyme is. You should know what substrate means. That's it. So see you in the next life.
Yes, baby, I've been drinking. I shouldn't come by, no. But I found myself in trouble, darling, and I had no place else to go. I got some whiskey from the barman, got some cocaine from a friend, and I had to keep on moving, baby, till I was back in your